The Strait of Hormuz represents the most critical hydrodynamic and geopolitical bottleneck on the planet. At its narrowest point, this transit corridor spans a mere 21 miles, creating an extreme operational maritime environment where spatial tolerances are severely restricted. Navigating this restricted cross-section is not merely a matter of tactical maneuvering. It is a profound test of applied hydrodynamics and structural engineering. Enter the Arleigh Burke-class guided missile destroyer, specifically assets like the USS Frank E. Peterson Jr. and USS Michael Murphy. These are not simply vessels. They are mobile, hyperdense industrial powerhouses engineered to operate within the most unforgiving physical parameters known to modern naval architecture. To understand the sheer scale of this engineering marvel, one must first analyze its foundational metrics. An Arleigh Burke-class destroyer possesses a full load displacement of approximately 9,700 tons. This immense mass is distributed across a hull measuring 155 meters in length, with a navigational draft of 9.3 meters. Displacing nearly 10,000 tons of seawater, while maintaining optimal kinetic efficiency, requires a hull design that minimizes hydrodynamic drag, while maximizing structural stability against turbulent ocean currents and severe maritime weather systems. The primary structural material of this floating fortress is high-strength low-alloy steel, specifically the HSLA 100 metallurgical classifications. Unlike standard commercial carbon steel, HSLA steel is alloyed with precise microscopic quantities of copper, nickel, and niobium. This chemical composition fundamentally alters the crystalline structure of the metal at a molecular level, significantly increasing its yield strength. The yield stress limit of HSLA, OI to 0, exceeds 80,000 pounds per square inch. In practical engineering terms, this means the hull can absorb massive amounts of kinetic energy and localized extreme pressure without undergoing permanent plastic deformation. When operating in environments where submerged acoustic and magnetic anomalies, such as irregularly deployed sea mines, pose a constant kinetic threat, the ability of the hull to absorb and dissipate underwater shock waves is paramount to preventing catastrophic structural failure. The construction of this hull requires a highly synchronized industrial assembly process. Massive steel plates are cold-rolled, shaped under immense hydraulic pressure, and joined using automated submerged arc welding techniques. The assembly takes place in specialized dry docks, utilizing heavy-duty gantry cranes capable of lifting prefabricated modular sections weighing hundreds of tons. The construction sequence follows a strict modular shipbuilding protocol. Entire compartments complete with pre-installed electrical conduits, high-pressure hydraulic piping, and heavy-duty ventilation ducts are manufactured in separate environmentally controlled facilities before being transported and integrated into the main hull structure. This parallel construction methodology demands extreme precision. The spatial connection points between modules must align with sub-millimeter accuracy. Every single weld seeing is subsequently subjected to rigorous ultrasonic and radiographic X-ray, non-destructive testing to detect any microscopic gas, inclusions or thermal stress fractures that could compromise the hulls. Integrity under the extreme hydrostatic pressure of the open ocean. Beneath the heavy steel armor lies the thermodynamic heart of the destroyer, a propulsion architecture built around 4 General Electric LM2500 marine gas turbines. These turbines are not standard maritime engines. They are highly advanced aeroderivative power plants, directly evolving from the high bypass turbofans used in heavy commercial aviation, meticulously re-engineered for the dense, corrosive marine environment. Operating in a combined gas and gas configuration, these 4 turbines collectively generate a staggering mechanical output of 100,000 shaft horsepower. The mechanical sequence begins within the compressor section, where multi-stage titanium alloy blades compress incoming atmospheric air to extremely high barometric pressures. This compressed, superheated air is then forced into the annular combustion chamber, where atomized marine diesel fuel is injected and continuously ignited. The resulting thermodynamic expansion generates a high-velocity exhaust gas flow that drives the power turbine rotors at thousands of revolutions per minute. Managing the thermal dynamics of this process is an engineering challenge of the highest order. The combustion temperatures inside the LM2500 routinely exceed 1000 degrees Celsius, a thermal threshold that would rapidly melt standard steel engine components. To mitigate this extreme thermal load, the turbine blades are cast from advanced nickel-based superalloys and coated with specialized thermal barrier ceramics. Furthermore, these blades utilize a sophisticated internal air cooling microarchitecture, where cooler bleed air from the compressor is circulated through microscopic internal channels within the blades themselves, forming a protective aerodynamic boundary layer of cooler air on the blade's external surface. The mechanical energy generated by these spinning turbines is transferred through a massive, complex main reduction gear assembly. This transmission system, precision machined with tolerances measured in 10,000ths of an inch, steps down the high rotational speed of the turbines to the optimal rotational speed required for the twin variable pitch propellers. This allows the 9,700-ton vessel to accelerate from a complete standstill to operational speeds exceeding 30 knots with remarkable mechanical efficiency. However, the LM2500 turbines do more than just provide kinetic thrust. A significant portion of their rotational energy is continuously diverted to 3 Rolls-Royce AG NOV Un-4.0 gas turbine generators. These generators produce the immense electrical baseline required to power the ship's internal grid. This localized electrical grid is capable of sustaining a small terrestrial city of 10,000 residents. This raw electrical output is the absolute prerequisite for powering the vessel's massive radar arrays, internal environmental controls, automated damage control systems, and the dense network of server racks that process millions of lines of code per second. Every rotation of the turbine blades, every transfer of thermal energy, and every kilowatt of electricity generated is meticulously monitored by an integrated engineering plant control system, ensuring that this floating industrial complex operates continuously at peak physical efficiency. With the massive electrical baseline established by the gas turbine generators, the Arleigh Burke-class destroyer powers its central nervous system, the Aegis Combat System. The core hardware of this system is the AN SPU multifunction phased array radar. Unlike conventional mechanically rotating radar dishes, the AN SPU utilizes 4 octagonal planar arrays seamlessly integrated into the ship's superstructure. Each of these arrays contains thousands of individual solid-state, radiating elements and phase shifters. By precisely controlling the timing or phase of the electromagnetic radio frequency signals emitted by these individual microelements, the radar system can steer the radiation beam electronically. This electromagnetic beam steering occurs at near the speed of light, completely eliminating the mechanical latency inherent in rotating antennas. The system operates on a processing cycle measured in mere milliseconds. It emits high-powered bursts of radiofrequency radiation, measuring the Doppler shift and transit time of the returning radar cross-section echoes. This allows the centralized command computers to simultaneously track and calculate the parabolic and sear-skimming trajectories of hundreds of independent aerial and surface contacts across thousands of square miles. The computational architecture dynamically allocates transmission modules to prioritize high-velocity incoming kinetic threats, ensuring a continuous, unbroken telemetry link. However, while the Aegis system establishes an impenetrable electromagnetic dome above the surface, the physical choke point of the Strait of Hormuz presents a far more insidious mechanical threat beneath the waterline: irregularly drifting, asymmetrical Naval mines. To neutralize this subsurface kinetic threat, the destroyer relies on the deployment of autonomous underwater vehicles, or AUVs, specifically platforms like the Knifefish Surface Mine Countermeasure System. The deployment sequence is a precisely choreographed logistical operation. The AUV, a heavily modified, torpedo-shaped drone, is lowered into the turbulent waters via a specialized hydraulic launch and recovery crane. Once submerged, the drone disconnects its physical tether and transitions to fully autonomous operational mode, powered by high-density lithium-ion battery banks. To navigate and scan the pitch-black, high-pressure environment of the seabed, the AUV utilizes a synthetic aperture sonar, or SAS, payload. Standard acoustic sonar is limited by the physical size of its transducer array. The SAS overcomes this physical limitation by computationally combining multiple acoustic pings emitted as the drone moves along a linear trajectory, effectively synthesizing a massive, virtual acoustic antenna. The drone emits low-frequency and high-frequency acoustic pulses that propagate through the water column. By continuously measuring the microsecond delays of the acoustic backscatter returning from the ocean floor, the onboard signal processors generate ultra-high-resolution, three-dimensional topological maps of the seabed. This acoustic imaging technique possesses a spatial resolution capable of identifying distinct geometric shapes and metallic densities, differentiating a half-buried unexploded ordnance from surrounding biological or geological formations. When the synthetic aperture sonar identifies a potential target, the engineering protocols shift from wide-area scanning to localized mechanical neutralization. The anatomy of these rogue mines typically involves a buoyant steel casing housing hundreds of pounds of high explosives, triggered by sophisticated magnetic or acoustic influence sensors designed to detect the ferrous mass or acoustic signature of a passing ship's hull. To safely neutralize this payload, the AUV approaches the target utilizing precision multi-axis microthrusters to maintain a stable hover against the underwater currents. The drone's onboard artificial intelligence analyzes the mine's orientation and calculates the optimal approach vector to avoid triggering the acoustic sensors. A specialized, highly articulated robotic manipulator arm is then extended from the drone's chassis. This robotic mechanism is an engineering marvel in its own right. Constructed from non-magnetic titanium alloys and carbon fiber composites to prevent premature detonation of the mine's magnetic fuse. The manipulator is equipped with specialized cutting tools and attachment brackets. The objective is either to mechanically sever the mooring cable, allowing the mine to float to the surface for safe explosive disposal, or to directly attach an engineered shaped explosive charge to the mine's casing. This attachment process requires extreme mechanical precision. The robotic arm, guided by short-range, high-frequency ultrasonic sensors, must align the shaped charge with the mine's surface, with a structural tolerance of just 0.01 millimeters. The entire sequence, from target identification to the final mechanical interaction, is executed entirely by the drone's localized processing architecture. There is no human operator remotely piloting the arm. The data latency of transmitting high-bandwidth control signals through the water column is simply too high. The AUV must autonomously solve the spatial geometry, adjust its microthrusters to counteract the hydrodynamic drag of the surrounding water, and execute the mechanical attachment flawlessly. Once the shape charge is secured, the drone retracts its manipulator arm, activates its main propulsion drive, and retreats to a calculated safe standoff distance. It then initiates the acoustic detonation signal, permanently neutralizing the explosive threat. The data gathered during these autonomous sorties is not lost. Every acoustic signature, every magnetic anomaly mapped, and every mechanical interaction recorded by the AUVs compressed and stored within its internal solid-state drives. Upon physical recovery by the Arleigh Burke destroyer, this massive dataset is immediately downloaded and fed into the ship's centralized tactical network. This continuous data fusion cycle allows the engineering teams to constantly refine their operational algorithms, adapting the AUV's behavioral software to counter increasingly complex subsurface anomalies. The deployment of these highly automated systems within the Strait of Hormuz is not conducted in a vacuum. It occurs within one of the most hostile hydrodynamic testing environments on Earth. Operating at depths approaching 100 meters, the autonomous underwater vehicles are subjected to immense hydrostatic pressure. For every 10 meters of depth, the ambient pressure increases by approximately 1 atmosphere. This means the AUV's titanium composite hull must continuously withstand crushing physical forces exceeding 147 pounds per square inch. Furthermore, the strait is characterized by severe tidal shifts, generating turbulent benthic currents with velocities frequently exceeding 3 knots. These subsurface currents create massive hydrodynamic shear forces that constantly threaten to destabilize the drone from its linear scanning trajectory. To counteract this physical displacement, the AUV relies on a sophisticated array of micro-electromechanical systems, specifically its internal gyroscopes and accelerometers. These sensors process spatial orientation data at thousands of cycles per second, instantly calculating the exact counterthrust required from the multi-axis propulsion modules. The continuous actuation of the microthrusters drains the high-density lithium-ion battery banks at an accelerated rate, demanding active thermal management systems to prevent internal cell degradation under heavy electrical load. This continuous mechanical balancing act, fighting against the immense weight and momentum of the ocean itself, is what allows the synthetic aperture sonar to maintain the ultra-stable platform necessary for millimeter-accurate topographical mapping. Simultaneously, the physical connection between the deployed AUVs and the command computers aboard the Arleigh Burke-class destroyer undergoes a continuous, rigorous stress test. Because standard electromagnetic radio waves cannot penetrate dense salt water, the entire command and control protocol relies entirely on an acoustic data link. This involves transmitting encoded data packets using modulated sound waves through the water column. However, the Hormuz environment is acoustically chaotic. Changes in water temperature, varying salinity levels, and the ambient mechanical noise generated by the massive propellers of the destroyer itself create severe acoustic multipath interference. The acoustic signals bounce off the seabed, the water surface, and thermal layers, arriving at the receiver out of phase and heavily degraded. To maintain data integrity under these extreme conditions, the engineering teams employ advanced digital signal processing algorithms, utilizing frequency-hopping spread spectrum techniques and forward error correction coding. This ensures that even if fragments of the acoustic data packet are lost to the ambient interference, the core telemetry and targeting commands remain intact, preventing a catastrophic loss of control over the autonomous drone. When this complex, multi-layered technological apparatus successfully neutralizes the submerged threats, the impact extends far beyond the immediate tactical perimeter. It directly manipulates the macro infrastructure of the global economy. The Strait of Hormuz is not just a geographic bottleneck. It is the central artery of international energy logistics, accommodating the transit of approximately 21 million barrels of crude oil every single day. When the physical safety of this corridor is compromised by rogue kinetic threats, the immediate mechanical consequence is the paralysis of ultra-large crude carriers. These supertankers, measuring over 300 meters in length and displacing hundreds of thousands of tons, require deep, unobstructed channels to maneuver safely. A single unverified metallic contact on the seabed can halt the movement of billions of dollars of raw industrial material. This paralysis instantly triggers a cascading failure across the global supply chain. Maritime insurance syndicates exponentially increase risk premiums, directly inflating the per-barrel cost of raw petrochemicals. By deploying the Arleigh Burke destroyers and their integrated autonomous mine countermeasure networks, the engineering capability of the modern naval architecture effectively reopens this locked corridor. It establishes a sanitized, verifiable maritime transit lane. This is not merely a localized military operation. It is the ultimate demonstration of applied engineering solving a macroeconomic crisis. The successful integration of Aegis phased array radar systems, combined with the microscopic mechanical precision of autonomous submersible robotics, proves humanity's capacity to overcome the physical limits of the maritime environment. By establishing physical control over the most critical choke point on the global map, this technological matrix stabilizes the international supply chain index and ensures the uninterrupted thermodynamic operation of the global industrial engine. If you want to dive deeper into the extreme engineering behind the megaprojects and machines shaping our world's infrastructure, make sure to subscribe and activate notifications to join our community of technical analysts.